We now talk about floating point numbers, and we notice that the numbers that we have been talking before about are called fixed point number formats because the position of a given symbol determines the value of the number that we are translating. So we normally say that the position is explicitly known. For instance, when we say 101, we know that the position 0, 1, 2 has a given value, and therefore we can be able to determine what value is represented by this number. On the contrary, we have floating point numbers, in which case the position of the symbols is not expressed in similar manner as that of fixed point numbers. And we notice that since fixed point has some advantages, which includes high precision and dynamic range, it still suffers some challenges of representing some figures that are particularly used in scientific applications. And for instance, when you are using a 2-bit sign magnitude scheme, you may use 16 bits to represent the whole part and the 16 bits to represent the fractional part. And in that case, you would be limited to representing numbers of the highest value of 65,000 and the smallest fractional part of 0.0001525, etc. This is quite limiting because you notice that some scientific requirements or applications have 10 to power minus 23 or 10 to power minus 15. Whenever you are representing some constants like the mass of an atom or Planck's constant, amongst others. So we notice that the fixed point number system is a little limited in representing some of these applications, and this becomes obvious that to represent such physical constants encountered in scientific measurements cannot be accommodated by the fixed point system. And therefore, that is why we require floating point numbers, and we say that a fixed point number scheme has several or serious limitations in the way we can store or process quantities with large dynamic ranges. And these limitations can be eliminated if you use floating point scheme because it uses scientific notation of number system. So we normally have a number that is expressed as A, and this A can be expressed as plus or minus m times r to power some exponent xp. And we say that any number, whether it is very small or very big, will take this standard format. And we notice that the m is referred to as the mantissa, the r is the base, and xp the exponent. So for instance, we have such a number as 7825,000. If you are to represent this number using a sign magnitude scheme with the 16 bits to represent whole part, this would be impossible. But when you represent it using the floating point numbers, you can simply express it as 7.5825 times 10 to power 7, and that number has high precision as well as high dynamic range. In similar manner, a very small number such as this one can be expressed in floating point with as negative 1.25 raised to power minus 6. Again, has high precision, and you can see the range between the two extremes is well accommodated in the floating point number system. A large exponent gives a higher magnitude, whereas a higher precision in the mantissa improves the overall accuracy.